Okay. First of all, I would like to thank the organizers for having me. It's my first time in Warsaw and it's a memorable trip. And in this presentation, I would like to introduce you with my recent paper, this one, which implemented the fast neutrino flavor conversion subgrid model to our Boltzmann code. And the collaborator is like Hiroki Nagakura and Shoichi Yamada. And Hiroki is gonna present on Wednesday. And please look forward to his talk also. And there are also several collaborators related to the Boltzmann supernova simulations. And as the previous presenters has already given great reviews, I don't have to introduce you in detail, but we are dealing with quark-class supernovae, which is the important ingredient for the cosmic chemical evolution and also responsible for the formation of compact objects. And we know that the massive stars collapse and bounce, and the propagation of the shock wave, you need neutrinos to heat up the matter behind the shock wave and make the supernova successful. So this is the schematic picture of the neutrinos inside the quark-collapse supernovae, and the yellow arrow is the neutrinos, and at the center, it frequently interacts with the surrounding matter, so it has isotropic momentum space distribution, and the energy distribution is simply Fermi-Dirac distribution. And as for the outer layers, it's simply free streaming. So the treatment of neutrinos in these two limits are simple, but for the intermediate region, it can have a non-trivial angular distribution like this. And in that case, the Boltzmann equation with respect to the phase space distribution function is necessary to solve, as the previous presenter has already explained. Since solving the Boltzmann equation is expensive, we have sometimes see the most popular approximate neutrino transport method is the M1 method, or truncate moment method. And this is the distribution function taken the angular moment in momentum space and truncate the higher order ones. So, and in order to close the equations, the analytical closures are usually used, but we don't know that how the moment method deviates from the Boltzmann ones, but in order to calibrate the closure relations, we need to solve the Boltzmann equations. So as a group, we are doing the Boltzmann radiation hydrodynamic simulation so far. And this is the equation we are solving right now. And Boltzmann equation for the phase space, neutrino phase space distribution, and the hydrodynamics equation, and neutrino matter interactions. And right now, these equations are general relativistic, and we are currently doing calculations with a spherical symmetric metric calculated from the spherical averaged hydrodynamical profile. And I would like to advertise our recent paper. This is done by a PhD student in Waseda University, and we calculated the rotating PNS profile and calculated the neutrino memory gravitation wave. And this is not the main topic of this talk, so I just show you one slide. And also, we are doing the series of 2D simulations, so I hope I will be able to report this result soon to you. So let's move on to the main topic. the collective neutrino oscillation part. So here's the neutrino quantum kinetic equations, and you have vacuum term, and matter term comes from the interaction with electrons, and there is a neutrino self-interaction terms. So as in the solar neutrino problem, the vacuum oscillation, MSW resonance, and matter suppression is known to be very important. But in supernova, since the neutrino density is so high, the collective neutrino oscillation is known to occur. And unlike these other phenomena, it's highly nonlinear and can be a time scale of like nanoseconds. So it is expected to have a large impact on core class supernovae. And I hope Hiroki is gonna give you more detailed review on collective neutrino oscillation on Wednesday. So please look forward to it again. And we are dealing with the fast neutrino flavor conversion. So it's one of collective oscillation modes, and the conversion timescale, as the name suggests, it's very fast and like nanoseconds. It's clearly much shorter than the dynamical timescale of neutrinos. And the electron type neutrinos mainly contribute to the neutrino heating. So if the fast neutrino FFC changes the flavor composition, it is expected to affect the supernova dynamics. And it is widely known that FFC is induced by angular crossing in momentum space. So this is the momentum space distribution, and this the right direction is the radial outward, and this left is the radial inward. And the solid line is the electron type neutrino, and the dashed line is the electron type antineutrino. And you can see there is a crossing here. So antineutrino is more forward peak in this region. So, and this kind of crossing is known to be the condition for the FFC. And by starting from this kind of profile, you obtain this kind of deformed angular profile. So this is what we want to know. What kind of effect this FFC has on core collapse supernovae. So the previous result was obtained by the quantum kinetic equation simulation, but since it is computationally too expensive, we implement subgrid model to the classical neutrino transport simulation, and we compare the three mixing methods with three names. This first one is it's meant for 4 species BGK, and this is the most robust method in our this result, and this is angular dependent mixing method. So as Masamichi Zaizen, he's present on tomorrow, and his calculation found that the FFC works to eliminate the crossing. So if you this kind of angular distribution eliminates this negative part. So inspired by this nonlinear evolution calculation, we implement the similar subgrid model to the classical neutrino transport, depending on the angular distribution. And the second one is the 3 species one. with the nu x equals nu x bar assumed. So this three species assumption is sometimes used in subgrid modeling of FSC. So I wanted to know the effects of this kind of assumption. And the third one is done by the Max Planck group and Jakob Ehring. And this is a simple equipartition method with the density threshold. And here is the computational setup. And I run the Supernova simulations with starting from the progenitor of 11.2 solar mass up to 270 milliseconds post bounce, and angle average the profile and restart the 1D simulation. And at the time the FF fast level instability appears, I restart. I also run the 1D simulation with the FFC subgrid model. So this is the result. This is the fiducial model, and I also tested the lower Y model with the electron fraction artificially lowered by 10%. So the top panel shows the shock radius, and the bottom panel is for the heating rate. And for the fiducial model, we didn't find any strong difference between models. But for the lower Y model, we found the difference for all models. And so this left figure shows the growth rate, and the right figure shows the electron lepton number and the heavy lepton type lepton number. And this red one is the four species BGK, and it can be seen that three species model show early appearance of the the growth rate is kept high in this compared to the four species BGK model. And also since the XLN is doesn't exist in the three species model, although this is the ELN for four species BGK, but the three species ELN shows the clearly different value. And this is the energy spectra with respect to the no FFC model. And this negative means that it's fewer, the number is fewer than the FFC model. So this is for nu and nu bar, which has the lower neutrinos converted to nu x, and these high neutrino energy ones are converted from nu x. So since the nu x usually has the higher average energy, so this kind of spectrum difference can be seen. And it is also worth mentioning that the three species models tend to overestimate the effects of FFC. And here I show also the heating rate and temperature profiles. And the green one shows the non-oscillation model. And other models, all of them show the enhanced cooling and the heating rate lowered. So as a summary, we implemented the subgrid model of fast flavor conversion to Boltzmann neutrino radiation hydrodynamic simulation and performed 1D supernova simulations. So for the model simulations, the fiducial model didn't show large difference with FFC, and with the lower Y model has the FFC have negative effects onto the collapse supernova dynamics. And the future prospects, since the we all know that the supernova is a multidimensional phenomena, so we need to do the multidimensional simulation. Since we are already doing a series of non-FFC models in 2D, we can probably start from the point with the FFI appears and see how FFC affects the supernova dynamics. And that's all for my presentation.
Thank you very much. Questions from the audience?
Thank you. I have a question about the duration of your simulations. In the last one of the last slides, I saw 40 milliseconds, 60, 80. Well, what's it? Yeah, 40 milliseconds. I don't think that you can draw conclusions on the influence for the explosion on such a short time scale.
Yes.
I mean, in the 11 solar mass, 11.2 solar mass model, for example, in the Ehring papers, we found that the FFCs can well help boosting and initiating the explosion. So this is too short, I think.
Yeah, and the reason why the time duration is not too long is that this is 1D, so FFI gradually disappeared. So we could. I agree. I totally agree with your opinion, and the final conclusion should be drawn with multidimensional simulations.
Are there any other questions, comments? If not, let's thank one.
Sorry. Yeah, another one. Sorry, I missed this. When you say 3 species and 4 species, in which respect do they differ? You certainly said it, but I didn't get it.
So this slide?
No, in general, when you say 3 species treatment and 4 species treatment, what differs between the two treatments?
Okay, so in the 3 species models, for the BGK model, I simply took the average of nu x and nu x bar as nu x. And so, and also in the density threshold method by Ehring didn't distinguish nu x and nu x bar, so that's the.
Oh, yeah, I think I understand what you want to say here, but the difference in the transport of nu x and nu x bar usually is quite small. It's weak magnetism corrections. Do you have that in your code? Do you use these opacities, including the corrections with respect to differences nu x bar?
Opacity is same for nu x bar in our
Okay,
code.
good.
Yeah, and
so what you merge here is mu's and tau's.
no, the difference of nu x and nu x bar only comes from the conversion from electron type ones.
But they convert pairwise, so I really still don't understand where your differences come from.
So
maybe this is very technical. Maybe we talk about that later. I really
okay.
don't understand if you don't use opacity differences, where your difference in the nu x and nu x bar comes from.
Okay.
Yeah, maybe we'll talk about that later.
If not, let's thank We'll continue with this talk by 4:30.